there is this one problem I find interesting enough to isolate as a special video. So it's called St. Petersburg's paradox. Perhaps you heard of it. This is the setup of this question. Imagine you take a fair coin and you toss the fair coin until it comes up heads. If the first time the coin came up heads was on the nth toss, you get 2 to the n dollars. So in particular, if the coin comes heads on the first toss, you win $2. If it comes heads on the second toss for the first time, you win 2 to the power of 2 or $4. If you had tails 3 times and then heads on the fourth trial, then you get 2 to the power of 4 or $16 and so on. And the question that we consider is, would you wage $1 million to play this game? Of course, right away many of you say, well, I don't have $1 million to wage, so it doesn't matter. But imagine that you have an infinite credit line. In other words, you only have to pay this credit line when you decide that you leave the game, that you no longer want to be part of it. So if you played once and you came at a loss, you want to play again, you can borrow another $1 million and another until you are satisfied and you want to settle your account, settle your score. You can borrow money until then. So think about it and don't play this video before you have thought about it for quite a long time. So the first question we should try to ask, how much money do we win if we play this game? How much per one round of this game? So let's try to analyze that. So x equals to 2 to the n minus 10 to the 6, where n is 1, 2, 3. Those are my possible payoffs. So if n is 1, I win 2 minus $1 million, because, well, I have to pay $1 million for each round. So what is the probability that I win 2 to the n dollars minus 10 to the 6? Well, that means that the coin came up tails for the first n minus 1 tosses and heads for the very last toss. So altogether the probability is 1 divided by 2 to the n. And the expected value, the average of winning per game, will be this sum. 2 to the n minus 10 to the 6 times 1/2 to the n. Now what is that number? That is the same as 1 minus 10 to the 6 over 2 to the n. If I add 1, it seems to itself many times, what do I get? I get infinity, and I subtract 10 to the 6 over 2 to the n, added for all the n. That will be just subtracting $1 million. So I win infinity minus $1 million, which means that you stand to win $1 million, no, not $1 million, you stand to win infinity dollars per game. Wow. So of course some of you are economically minded and you are worried about inflation. And you cannot have infinite amount of money to begin with, and even if you could, perhaps that will make the money worthless. Let's ignore that fact, right? That just means, let's say that you become superbly infinitely rich. Maybe it's a casino, interstellar casino, where you can get all the riches in an infinite number of galaxies. Do you want to play this game? Did you have any reservations in plunging into this game, in investing your money, or taking the indefinite loan? Perhaps this modified game might help you understand why you might have felt those reservations. So let's avoid the problem of inflation and restrict the game to be played at most n rounds, capital N rounds. So the coin now cannot be tossed more than capital N rounds, and let's say this is what's going to happen. So we toss the coin until it comes heads, if the number of times we have to toss it is less than capital N. In that case, you win 2 to the power of n dollars. If you tossed the coin all the way until capital N and it were all tails, and then you just win 2 to the power of n plus 1 dollars. How many number of tosses should we allow the coin in order to make the game profitable on average to the player? So we can make those calculations, right? So the winnings you will get if the number of rounds were less than n, then capital N will be 2 to the n minus 10 to the 6. Now, if you happen to win 2 to the power of n plus 1 dollars, that means what's the probability for that happening? That would be 1 minus the sum of the probabilities that you did not receive, that you didn't get a head before. So that is 1 minus the probability that a head came earlier. And that number clearly equals to 1 over 2 to the power of capital N. That means that the expected value, your average winning per game, will be this calculation. This sum means that you rolled up heads before you reached capital N. And this means that you only receive tails. So you look at the summation, 1 over 2 to the n times this is just going to be 1. 1 added to itself, capital N times is capital N. This gives you the extra 1. And if I sum 10 to the 6 over 1 over 2 to the n, with this part, it ends up being 10 to the 6. So the game, to be profitable, has to have at least 10 to the power of 6 minus 1 rounds. Minus 1 is 0, so it actually has to have at least 10 to the power of 6 rounds to be profitable. Now what does it mean? It means that in order for this game to eventually pay off, you have to allow the coin to come up heads first time on the 10th to the power of 6th on the millionth round. The probability that this will happen is 1 divided by 2 to the power of 10 to the 6th. So this probability is so unbelievably, so minute that it is just impossible to fathom. Just for comparison, there are 10 to the power of 82, at most 10 to the power of 82 atoms in the entire universe. This number, 2 to the power of million, is enormously, unbelievably larger than 10 to the 82. So the thing is with this game is that you have to play so many rounds to actually come up victorious, to actually start getting a payoff, that it's beyond human comprehension. It is, for any finite being, the same as waiting forever. So as we are finite beings and we have very few years to live, very few days to exist, even if we had many days by comparison, any geological scale by comparison, any universal scale by comparison is too short. It's like an eye blink compared to the likelihood that a fair coin will come up heads for the first time on the millionth throw. And that's a probability, that's a possibility that must be included for the game to eventually be profitable. So that means that it's not always true that we want to maximize expected value, because sometimes to maximize expected value will take an infinite amount of energy, an infinite amount of time.